June 2023, and before that, I was a research. This same study found that 34% of this NPP growth was 2008 to 2016. And during this period, we have added cropland array of over 1 million acres per year. And they also looked at the yield performance of these expanded croplands, and unfortunately, they are not performing very well. 70% of these expanded cropland perform below the national average with an yield deficit of these carbon came from soils. And talking about carbon emissions, which contributes to global warming, these animations here showing the global warming across the globe since 1880. And research conducted by NASA found that global surface temperature was warmest in 2023, and the past few years have been the warmest of the 140-year period. We all are experiencing record-breaking hot weather over the last few years. July to December, every month, it's setting new records for high temperature. And we humans are mostly responsible for this unprecedented global warming. By fossil fuel burning, by unsustainable land management, we are emitting carbon dioxide to the atmosphere and thickening its carbon concentration. Even during the COVID-related economic shutdown in 2020, the global atmospheric carbon dioxide concentration was 412 ppm in 2020. And the last reading in July 2024 was 426 ppm. So it's increasing. So climate change solutions is at now or later stage. And luckily, we have a thin layer of soil blanketing the Earth. So in the atmosphere, roughly we have about 830 petagram of carbon now. And the top 2 layers of soil can store carbon in the range of 1,500 to 2,400 petagram. With regenerative and sustainable practices, we can store a large amount of carbon in the soil to help with climate change. And therefore, in 2015, at the COP21 conference in Paris, the global community agreed on an initiative called 4 per mil, that is increasing the global organic matter stock by 0.4% every year. Although it's quite ambitious, but it also highlights the importance of restoring soil carbon in our agricultural landscape. And that recently resulted in an emergence of soil carbon trading markets across the globe. But the question is why farmers would be interested in sequestering carbon in their farmland. Although soil carbon is an important strategy for natural climate solutions, it's also an important soil quality parameter and helps with crop productivity. So it enhances soil water holding capacity and infiltration, both of which are very important for soil water dynamics and management. It helps with soil tilt, it helps with nutrient cycling and storage, and disease resilience. And all of these contribute to better crop health and productivity. And help with adapting with the climatic perturbations like changes in precipitation pattern, all the summer droughts we are experiencing these days. So sequestering carbon in the soil not only help with climate change mitigation, but also adapting with the climate change. But the challenge is soil organic carbon and related soil health parameters are very sensitive to changes in land use, land cover, and agricultural management. In this animation, I gathered time series Landsat satellite data since 1984 around Lafayette, Indiana, which is displaying the dynamics we can see across the land. And capturing those variability is very important to inform our decision for site-specific management. And some of these we can achieve with data-driven agricultural practices. In recent years, smart farming using different geospatial data set has been highlighted by the scientists and the experts, and we are adopting it across the globe to help with more precision management, more sustainable management practices. And what are the tools that are making data-driven digital practices more powerful these days? Any guess what we are seeing in this video now? Space junk satellites. Space junk satellites, yes. So all these red dots in the map is showing different satellites. And I recently downloaded it. So this website updates stuff in space pretty much every day. So you can see a real-time view of the satellites that's scanning the globe. If you have any favorite satellite, you can search the name and it will show you where it is now. So this is really cool. But what I'm trying to highlight here, there are like hundreds of satellites collecting terabytes of data set every day, which we can really utilize for our land management practices. And if you closely look at these two graphs, which are showing different satellite missions run by NASA on the left panel, and on the right, different satellite missions from European Space Agency. And you can see last 5 to 10 years, they have been adding lots of satellite missions and more are coming. So that's why people are calling it golden era of Earth observation data missions and collections. So, and we should be utilizing these geoinformations for our site-specific management or sustainable management in agriculture. And if you want to add to that list, these amazing drone technologies, the global satellite navigation systems, proximals and infrared sensors, and really immensely powerful computational facilities these days, making digital agriculture extremely powerful. And we should be leveraging on these tools and facilities for sustainable agriculture. And another important advancement is digital soil mapping that is also a product derived from geoinformation systems at various scales. The digital soil map produces high quality, valuable soil information from field to landscape scales. But what is a soil map? So soil map is a geographical, is a two-dimensional document showing geographical distribution of different soil classes and soil properties. So in the background of this slide, you are seeing a soil map showing different soil classes in sharply marked colors. And soil maps can be utilized for different purposes, like answering from basic questions, where we need to install subsurface drainage, where we need to put fertilizers, or things like, is this land suitable for agriculture even? We don't want to farm a land with large rocks and really poor organic matter, right? So this could be gathered from soil maps. And there are like myriad of other uses of soil maps. And many of you are probably familiar with this map, the USDA Web Soil Survey, which is a repository of country scale soil information products. So all these yellow polygons you're seeing are showing different map units. And then there is Purdue Soil Explorer. So this is a Purdue Purdue product developed by our very own Dr. Daryl Schultz. So this product actually extended what we have on the USDA Sargo data set and combined that with high resolution LiDAR-derived digital elevation model to visualize and better understand the soil geomorphic relationship. So in this map here, you're seeing the dominant parent materials across Indiana. So although these soil map products, what we have now, are providing valuable information, they come with some important limitations. So I want to highlight some of those here so that you understand what we can gain from a digital soil mapping. So for example, here in this map, you're seeing some portion of Clinton County in Indiana. So in this map, the largest polygon covers an area of 1 square kilometer. So anything within that 1 square kilometer area, we cannot detect those spatial variability. So all these traditional soil maps comes with this spatial overgeneralization. While digital soil map can be produced as a continuous raster map representing individual soil property, as you are seeing on the other side, where I'm showing a digital soil map of soil salinity across one of my study area at 5 meter spatial resolution. So you can see the variability every 5 meters in that map. And this is also when you need to produce maps for field scale management, we may probably need to produce maps at that resolution, but when you need something at a regional scale, we can produce the maps at 100 meter, 200 meter spatial resolution as well. So that's a really great advantage of digital soil maps. And another challenge with traditional soil mapping is the map products are based on the mental models of the soil surveyor. So depending on who is surveying and who is producing the map product could be quite different, and we won't be able to assess the uncertainty. While in digital soil mapping, we produce a map based on statistical and mathematical models, so we can confidently identify the uncertainty of that map product, and it's really helpful for the utilization of the map for our practical solutions. So this is a general framework of digital soil mapping where we use data set from different sensors, mostly remote sensing, and that we can inform those data set using field and lab-based data in predictive models to produce continuous representation of different soil properties at various scales. So with this continued advancement in geospatial data gathering technology, computational facilities, and tools like digital soil mapping. Geoinformatics has become extremely powerful these days and can help with site-specific management and to inform regenerative agricultural practices in multiple ways. So in the next few slides, I will be demonstrating how I leverage these tools in my research. So in this slide, I'm going to be presenting a study from British Columbia, Canada, Lower Fraser Valley, British Columbia, Canada. So this study area is agricultural hub for the province and produces more than 50% of its production annually. So over the last few decades, this has been intensively farmed and probably caused a sizable change in land use land cover and loss of soil organic carbon. And the climate model also predicted that by 2050, we'll be seeing a substantial rise in temperature and precipitation, which may cause substantial challenge for agricultural soil management, given that soil in that region is characterized by poor drainage and workable conditions. So coming up with site-specific management strategies at field to landscape scale is an immediate priority of this region. So in this project, we wanted to look at the spatiotemporal dynamics of soil carbon, land use, land cover, climate across the valley from 1984 to 2018. And this schematic here is showing how we performed this analysis, where we put together time series Landsat satellite images since 1984. We put together climate model predicted data set, existing soil survey variables, and digital elevation model to identify the spatiotemporal interaction between these parameters. And this is what we came up with. So this map is showing the absolute change in soil organic carbon between 1984 and 2018. And anything green in this map is soil carbon gain, which is almost non-existent. And anything red is soil carbon loss, and yellow is somewhere in between. And so we estimated that about 61% of this landscape lost carbon during this period, while 12% exhibited increase in carbon and 27% remain unchanged. But altogether, there was a loss of 5.8 megaton of carbon dioxide equivalent during this period. And when we closely look at where those soil carbon changes were coming from, or loss were coming from, it was really in the annual cropping, the lands which has not been changed during this period. So that identifies that we have been really intensively farming this annual cropland in this valley, and we need to highlight the importance of regenerative practices in this landscape going forward. But we also observe some hope with some of these land use practices, like when annual cropping were rotated with grassland, or annual cropping was being converted to perennial cropping. It was showing some increases in soil carbon, and we were really hoping, probably a future study can tell, if these land management practices are actually accruing carbon over the years. So I'm now going to take you to Sweden for a study where we utilize geoinformatics to map soil wetness across the country. So soil moisture information is highly important, but they're not available all the time due to different limited data options. But with the advancement of lighter data collection technologies at national scale, this has become quite important. Like, at least we can now make products that can show where we likely see more soil moisture over the other areas. So, and then we can connect these sort of data products with like more temporal resolution, satellite information to study the variability of soil moisture across the country. So why it was important in Sweden? So Sweden has one of the mostly modified boreal landscape of the world, and about 80% of the channel network across the country are human-made. So they were dug over the 100 years or so. And government now is putting a lot of effort into how they can restore some of those great wetlands. But they don't have information on how the minerals and peat salts are distributed across the country, which channels are man-made or which channels are natural, so that they can site-specifically manage those restoration efforts. So this is what we try to do in this project. So we produced soil wetness map across Sweden at 2 meter spatial resolution. That's what you were seeing here. And then we worked on this map to develop a few of the products. For example, in this graph you were showing, we established a model relationship between different organic soil thickness and soil moisture. And based on that, we produced a distribution of peat soil and mineral soil across the country at 2 meter spatial resolution. And then we are also trying to produce these sort of maps as well. So we are reconstructing digital elevation model, high resolution light derived digital elevation model to produce the prehistoric landscape. So what you are seeing on the left is the channel network before any human modification happened. And what you are seeing on the right is the current conditions with tons of new channels that have been added, which are dug by the humans. So we need to have those precise information to better know where we are putting our restoration efforts, and those will be helpful for better climate change mitigation for the country. So governments are currently using these data set we developed in this project for running those experiments across the country, and they're also helping with digital forestry and digital agricultural applications as well. So taking all these experiences from other countries, I just established a lab at Purdue University to develop and apply innovative geoinformatics-based approaches to study soil and agroecosystem at field to landscape scale to support climate change mitigation and adaptation. So in the next few slides, I'll be talking about some of the projects that my students and postdocs are conducting, but don't get excited about seeing some results because my lab is just five months or so old. So we are just trying to deploy some of the recent projects in different parts of Indiana. So for example, here, two of my students, Omiya and Li Jiang, they're working on Purdue agricultural centers. So Omiya's project is looking at spatiotemporal modeling of soil carbon dynamics and crop yield at farm scale. And Li Jiang's project is looking at benchmarking soil health between conventional and regenerative agricultural management at different Purdue Ag centers. Li Jiang will be start collecting soil samples from all of these tracks starting next week. So we are hoping to produce some good results in the next year or so. So a little bit about Omiya's project for modeling the dynamics of soil carbon and crop yield. So we are gathering historical soil sample data from acre since 2016 to 2024. And then we are producing soil organic carbon maps at different time steps during this 10-year period. We are also collating crop yield data set from harvester and predicting crop yield across the farm during this period as well. And at the end, we would like to answer questions like, what are the practices in acre are helping with soil organic carbon gains or losses? And if we are gaining, does these gain soil carbon credits convert into crop yields at farm level? And in another project, my postdoc Fitzum, who just joined 4 weeks ago, right, Fitzum? Yeah. So he became part of a large project led by Dr. Icha Rui at our department. So the Fitzum will be looking at geospatial modeling of soil health parameters under different organic management practices. So this map is showing organic farms distribution across the state. And we collected some baseline soil data with the help from Dr. Rui's students. So this year, our plan is to identify some farms across the state where we'll be doing more in-depth data collection and modeling in the coming 2 years. And my other student, Nelson, took a different route. So also he loved to make colorful, beautiful maps, but he also thinks it's important to identify the optimum sample location for producing these maps. So as you are seeing in this video, our landscape is really variable and dynamic and heterogeneous. So capturing those variability during the soil sampling phase is very important to devise site-specific management decisions and soil mapping. So Nelson's work will contribute to that. And the general notion is that if we increase the number of sample points, that should capture higher spatial variability. But that will also increase the sampling efforts and costs. So our hypothesis is that there will be an optimum point after which increasing the number of samples will not equally capture more spatial variability. And there is a really small body of research on this topic, and Nelson is currently conducting a literature review of what are the techniques that are available. And at the end, we want to build a prototype tools for the farmers in Indiana so that they can draw a map, draw a polygon of their farm field, and that should show them where the optimum locations for soil sampling for their soil health analysis. Or if we go after a landscape, probably we can produce optimum location for soil sampling for regional scale soil mapping. So that's the plan. And my other student who just came from India, and he'll be here with us for a year and a half. And he came with a large data set collected across the Indo-Gangetic Plain in India, which is one of the main agricultural producing region in the country. So during his time here, he'll be developing 2 products. The first one will be utilizing cell phone images for cost-effective prediction of soil health parameters using deep learning models. And this is going to be a really important product for countries, different developing countries, where cost efficiency is more important than what we see here. And then he is also interested in developing a regional scale decision support system to recommend best management practices for enhanced soil health using time-series satellite data and AI. So that's pretty much summarizes what we're working on. And I'm hoping in the next year or two, my students or postdoc and I will inform you about some of the exciting results we are producing about that. And so I also wanted to talk a bit more about my teaching program at Purdue. And I'm starting a new course in spring 2025. And with no surprise, that's going to be geospatial informatics. And I'll be teaching that course. My target audience students are mainly senior undergrads and grad students. So I talked with faculty members across the campus teaching remote sensing and GIS, and I was informed that we need a mid-level course which connect the bridge between more introductory and more senior level courses. So that's where the ideas of this course came from. So the overview of this course is to advancing the course will cover topics in geospatial science, emphasizing practical application for soil agriculture and natural resources management. I want to teach students different cutting-edge tools in GIS and remote sensing so that they are better equipped with site-specific and sustainable soil management, precision agriculture, and environmental sustainability related works. So the course will have both lecture and labs. And I'll be covering topics like emerging remote sensing techniques like hyperspectral remote sensing, LiDAR-based remote sensing, different digital elevation models, global satellite navigation system, cloud computing, and obviously I want to spend time some lectures on digital soil mapping and site-specific management. And there'll be complementary lab sections for all of this topic. So the course will have some prerequisites, which so these are some of the courses I listed, which could be complementary for this course. But for grad students, we can always waive these requirements if needed, or maybe other students who came from other universities, these requirements could be waived. So coming back to James again, so how we are placing ourselves into the future. So stakeholder decision-making is heavily reliant on the cost benefits of an planned or implemented strategy. But with climate change related initiatives, this is harder to get those information all the time. And especially when it's easy to adopt a management practice when we can see the short-term benefits. But it's harder, decision-making is harder when the implemented benefits are not short-term, rather it requires longer time period to accrue the benefits. And so for any initiative related to climate change adaptation and mitigation, regenerative practices, it requires time. For example, the national climate solutions using soil organic carbon sequestration may not happen overnight. So it will require time. So there are some trade-offs and synergies between these initiatives. And at James Lab, by leveraging the advanced Earth observation tool and digital innovation practices, we would like to produce products and information in that sphere so that we can identify those synergies and trade-offs of different regenerative and sustainable practices and support climate change adaptation and mitigation across the board in agriculture. So with that, I would acknowledge my amazing funding sources. And I'll be happy to take a question. And I wanted to put that together so that you know which was coming.
Good, thank you so much. One of the really nice things about this series, it gives us a chance to meet both existing faculty and junior faculty as they come in. And we're actually having meetings throughout the day to talk about the opportunity to interface with the geoinformatics program in a new way and the new additions that he's able to make. And so I actually really appreciated hearing more about the class that he's going to be providing in terms of providing a diversity of perspectives in sort of the digital agriculture space. So thank you very much, Siddhartho. Are there any, Kevin, did I see you had your hand up?
Yeah, so something that I've seen as an issue is sort of prior use of kind of the ag experimentation effect. And also the cases where, we saw evidence based on yield maps. Somebody had like a farm road, in their field, drain piles, sort of these human changes to the environment, which you talked about with your, drainage ditches or digging out, grandpa was digging them out by hand. So how do you account for these historical artifacts on top of the kind of geomorphology aspects?
That's a very good question. So in some of the experimental station, we are also lucky that we have historical data set, historical air photographs, historical images captured at different times, and also the wealth of knowledge you get walking across the hallway, right? So for example, currently my student who is working on the crop yield map in Acre, we are working on those, filtering out those data set that's like misreporting, like yield from a tile or, from a tile drain or from a walkaway. So like doing those, detective work is important. It's not like building or predicting a model using the machines. It's also like doing those detective work and looking at our products, validating with historical information. And I'm not sure if I have highlighted that. In some of my maps, I tried to use data from 1980s, soil map that was collected in 1980s, so that I have confidence in the map products I developed, which is not possible in all cases, but as much as we can leverage those information. And I also want to highlight, probably I forgot to mention, like when I was comparing between traditional soil map and digital soil map, I forgot to mention that we can product valuable input from this traditional soil map for our digital soil mapping models. Like things like texture does not change. things like soil parameter does not change. We can extract those information from historical soil maps and survey.
Great, thanks.
Yes.
It seemed like quite a bit of your work was on a fairly large scale, you showed regions and such, and I'm curious what you're doing more on a micro scale, like on a within field scale. Like if a farmer knew that there was more wetness in this particular spot, of course, I'm sure they intuitively knew that. But could they manage stuff differently there with the fertilizers perhaps, or lots of other inputs? What are you doing in that area?
So like, I think I would say 80% of my current project in the lab, like 5-6 of them are focused on farm level management.
Okay.
So we are like really fortunate to have these high resolution data set, LiDAR data, hyperspectral imaging data, UAV data set. So I'm trying to leverage those tools for producing products that will be more valuable at farm scale. But also, I love to use temporal satellite data information. So with Sentinel satellite, for example, we can produce products at 10-meter spatial resolution over the last 10 years. So I not want to, discard those valuable information or farm management that we can extract from satellite image. And then we can connect those with the high resolution data products so that farmers are more benefits. Yes, Brian.
Excellent.
Yeah, I can have that relates to Bruce's question. So you talked about some soil moisture data product, right? I was just curious, like, what is the temporal scale or resolution of that data?
So the map I showed there, it's a static map. It doesn't have any dynamic information. It's just showing us based on the soil texture and organic matter or related properties where we can expect higher wetness versus which areas are just dry. And then we can combine those information with time series satellite data. We are collecting data for pretty much every day, but at a really high resolution, really close resolution, like we are talking about kilometer resolution.
So, well, just we follow up. So, like Bruce said, at a field level, we see a lot of variability in soil moisture day to day, and it's one of the most difficult aspects to model.
I think proximal sensor or in situ sensor would be a way to go for that. We don't have any satellite data yet.
Is there a way to predict? Okay, this could be a wet area versus dry area based on the other static soil information.
Yes. I did some work in that space as well. So we produce soil workability maps. That's basically telling us the soil plasticity limits. So where we are expecting more wetness versus where we are not, and how that relate with more real-time information collected from in situ or proximal sensors. But soil moisture is always a tricky thing to deal with.
Moisture.
Yes, Kevin.
So if we're trying to use these generally to make policy decisions or very broad scale or regional or global decisions. But old soil maps, they have county boundaries or state boundaries and, so how do we move from that kind of that political boundary issue to a more consistent, spreading out digital maps that are available?
So I think to address that, we need to use sensors that goes beyond those boundaries, right? So I'm talking about satellites. So satellites doesn't see any boundary. I'm not sure about North Korea, what we will get there. But like for our country, we can produce satellite data set and then probably we can feed in where our road networks were, even networks were, that we manually digitize across the country to update those information. But that's the whole aspect of producing digital soil maps, because it's going to be continuous maps. But if you look at some of the product developed by FAO for global scale, you'll see some of those boundaries. I was looking at the boundary between United States and Canada. There are quite a bit of uncertainty. You can literally tell, okay, here is the national boundary. but soil doesn't behave that way, right?
Okay.
Yeah, that's not the only, that's not the problem with only soils, but even like yield maps and yield data that are published come from a administrative region, and that's always a like so. For instance, like the northernmost part of Indiana would be closer to Illinois than the southernmost part of Indiana, but the data are reported on a state basis, so. I don't know how to.
Help us.
Dr. Paul.
Yes.
In the 1960s, Purdue started a really famous program called the LARS lab. You said that's a laboratory for remote sensing. They collected lots of historical data. What are the opportunities to combine some of this older historical data with newer or the newest forms of satellite and other forms of remote sensing data?
I would say one of the major focus of my work is to utilize some of those data sets. Like when Ron was interviewing me for this position, I asked, I need access to historical information. I need to archive soil samples. I need to have access to different archive data set that was produced. And LARS is one of the initiatives that produced probably first satellite-derived soil maps in Indiana. So I'd be really excited to incorporate some of those information. And I think I already talked to Dr. Melba Crawford, about utilizing some of those data sets for Indiana specific models. And we'll see how those play with the models, the new territorial models.
So those data are relatively easily accessible for.
That I'm not 100% sure yet, but like many of the soil data sets that were collected by USDA, those are available. And in some of my proposed project, I've been in touch with USDA National Soil Survey people, and they're willing to provide data set they have been collecting at different time. Yes.
You said that your student from India wants to collect like some soil information with cell phone images. I am wondering if you can share, of course, like how do you plan to do that? Because when you're getting information from satellite images, you're using like some kind of sensors that allows them to get like those data to get like index and so on. So I am curious to know how are you planning to do that with cell phones?
Okay. So so this is still in the really initial phase, but how we are working on it. So before the student arrived here, he air dried, ground all the soil samples, took it into a black box, and took images with cell phone, so that there is no light pollutions coming into that. And then we are now processing those images, RGB, those are red, green, blue images, right? So we are processing those images now to identify different index that we are hoping would be related to some of the soil property variation. So yeah, like those will probably come with some uncertainties or maybe large uncertainties, but we will know when we build the models. And like when we don't have any data set, it's still good to have some data, probably with larger uncertainty.
Any final questions for Dr. Paul? Why don't we say thank you once again. Thank you all for coming. So could you jump back to the first slide you had up? It was this is the data-driven seminar series. We have a series of speakers coming up in coming weeks. Some focusing on forestry, plant science, some local and some more broadly represented. So pay attention to the coming speakers, and we'll see you in coming weeks. Thank you very much.